Hi everyone! In week 13, we were looking at the topic of environmental health. And there are a whole host of different topics that we could have dove into for lab this week, but what we're going to look at specifically is we're going to look at disease and disease transmission, which is sort of a very timely lesson considering that we are in the midst of a global pandemic with a novel virus that has certainly caused a host of health complications. It's caused a host of deaths, both nationally and worldwide. And it's something that is difficult to contain for a lot of different reasons. What this lab is going to do is it's going to give you an idea, a simulation of how diseases spread in a population. And we're going to be looking at a few different types of diseases this time, and we can kind of relate them to things that we're familiar with. So in the first part of the simulation, we're going to take a look at a disease called the cold, spelt K-O-L-D, right? So this is a particular type of disease that is fairly infectious. Infectious means that it's pretty easy to spread. You're not sick for a very long time typically, so you're typically only sick for about 5 days with this particular disease, and you have few, if any, deaths as a result of having a cold, right? It's not very common you would find someone who died of complications related to catching a cold. So this is sort of your simple, average, easily spread type disease. It doesn't have, again, important health consequences, but it is something that is persistent in the population. So what you'll do is you will click on the link to the Disease Lab Simulator, and you're going to want to make sure that in the lesson box up here you are in the Virgin field. This is where we're going to be. And for each of these diseases, we have different types of parameters that we can change. So what we're looking at is we want to know what the impact of things like population size, population density, population mixing, what impact does it have on how a disease spreads. So in this particular lesson, again, you can click on details here for things if you want to know things, but we're going to leave these parameters set. So you're sick or contagious for 5 days when you catch the cold. The transmission rate is 10%. So that means if you're exposed to 10 people, one of them is going to get the disease. And again, we're going to say the death rate on this is 0. Nobody's dying of a cold in this example. So in our first scenario here, we're going to go ahead and look at the cold, and we're going to, in this simulation, we're going to look at how population density impacts how the cold spreads. So coming back to our simulation, we've got low population, which is 200 people, a medium population, which is 600, and a high population, which is 900. And the little green dots are in our population who are representing our population here. So all of these dots, these 900 dots represents individuals. And as you can see, regardless of where we start, we always have a couple of individuals who start sort of the transmission, right? So someone initially has to be infected. So these are our patient zeros, if you want to think of them that way. So in each density here, low, medium, and high, we are always starting out with 3 individuals. So the next thing we want to look at is we want to look at our population mixing. So we're going to keep our population mixing standard, and we're going to do a medium population mixing. So what that means is in medium population mixing, it means that you're not just staying home and only interacting with the members of your household. So that would be a case of very low population mixing. Medium population mixing would sort of be average. You might go to school, you might go to work or to a job, but we're probably not getting together in huge groups. So you wouldn't be going to large sporting events or large concerts or things like that, right? So we're doing sort of this medium amount of population mixing, which means we're leaving our homes, we're interacting with other people on a day-to-day basis, but we're not interacting with very, very large groups of people. So then what we'll do is we're going to run the simulation at these 3 different densities 3 times each. So low, medium, and high. And the reason I have you run it 3 times is because you'll notice that the data is different every single time you run this. So I'm going to go back to a low density, which is where we start this, and I'm going to go hit the run button. And we're going to watch it go through. And again, it was very fast. If you blink, you missed it in a low population. But what you see is that down here, here's sort of the data that we're going to collect from this graph down here. And then we also have some information up here. So what we're going to keep track of in this simulation is we're going to keep track of sick days. So sick days is a measure of, in the entire population, how many days did we have sick people in our population? Okay, so this ran for 100 days is how long our simulation runs. And for 42 days out of the 100 days, people were sick in our population. Per capita is simply, if you were to break down the number of sick days divided by the number of people in the population, that's your per capita. It roughly means, again, how many days each person was sick. Again, it's a rough estimate. Obviously, you're not sick for 0.2 of a day, but it's just another way to sort of look at overall numbers in a population as far as, again, we're looking at rates of transmission here. So the lower this number is, this per capita number is, the less this disease is probably being transmitted. And then again, from here, what we can also tell is that very quickly we had the most people contagious, right? It peaked early at about day 4, and there were 8 people contagious. And then the graph dramatically went down. We were down to just 1 person. Eventually, you'll note that we had a few immunity cases here in the population. So they're the blue folks, right? So these are the folks who, as it turned out, they didn't get sick. They came in contact with it. They could have potentially passed it on, but they themselves didn't catch it. And there are no deaths here. So I'd go back to my table and I would put in for run 1 this data, right? The population number, the sick days, the sick days per capita, the max contagious. So again, that came from the graph down here at the bottom. The max number of contagious in this case was 8. So I would write that down. The number of immune at 100 days and the number of at risk at 100 days. So the number of immune and the number of at risk, the at risk people are in green here. So there's still 191 people who are at risk after day 100. And there's only 9 people who are immune. So it essentially means that, again, the cold is something that there's so many different versions of the cold and you can catch it multiple times. So even if you've had it, you're almost always at risk for catching another cold, right? And this is pretty true of what we see in the winter. You can catch multiple colds. So what's interesting is when you hit reset, and if you run that simulation again, it looks differently this time, right? So I kept the parameters all the same, but you'll notice that I have more sick days. My per capita rate is a little bit higher. I actually have more people who are immune this time, and I sort of had different peaks as far as how many people were contagious when. So there's variability in this model so that every time you run it, you're going to get something slightly different. It will never be the same data twice. So again, for the whole first part of the lab, you're just going to change the population density each time. You're going to leave population mixing the same, and you're going to leave the disease the same. Okay, so that's the first part. So you'll look at something mild like a cold. Then we're going to take a look at something different. So let's take a look now at a different disease, and this disease is called the influenza, right? So it parallels the influenza, the flu. What do we know about the flu? Well, what we know about the flu is, let's go ahead and change to influenza here, and we're going to reset everything. Looking at the details, we know that the transmission rate is higher, so it's doubled the rate of the cold. We have a death rate now because people do die from the flu every year, but we have a shorter period of time where you're essentially contagious, where you can pass it on to other people. So rather than that 5 days that we had with the cold, now we're down to 3 days that we can pass this along. So we're going to do the exact same thing. This time we're going to actually look at how population mixing impacts transmission rates. So again, now my population number is going to be high, my density, but my mixing is going to change from no mixing, which means I stay in my house and I never leave my house, kind of like the emergency order that we were all back in, your stay-at-home shelter-in-place order. That would be no mixing at all. Low would be when we started to first come out of that order, where we could go out, but again, you couldn't eat in restaurants, and you should stay home as much as you can still, and you could do some shopping but very little. That was sort of this low mixing. Medium is what we're in now, I would say. Well, what we were in before the new restrictions have now taken place again, where once again indoor dining isn't allowed, but where you can still go out a little bit more. Some jobs, some schools. And then high mixing again is sort of your normal, if things were back to normal, that's what a high mixing population would look like. So, excuse me, back to the simulation. So our density is high. Our population mixing is none at the moment. We're going to hit the run button, and we're going to watch the disease spread through the population. And again, what you see is that we have a huge spike, even though once again, we're not mixing very much. We have a big spike here at the very beginning. So now we have a new line on here. This is our death toll line. Okay, so not just the 3 lines we saw before. Now we have a death toll line as well. And again, what you're looking at is the death toll. We have that in a percentage as well. How many days people in the population were sick. And again, sick days per capita, just as before. So once again, you'll put all that information in the table as before. You'll answer specific questions about that. And then last but not least, we're going to look at what happens if we were looking at a disease for which there was a vaccination, and how do vaccination rates change these numbers? So what you'll do now is you're going to actually click on vaccination, and you'll see that a new field here has popped up, and you're going to put in parameters for the disease. We're using a different disease. This particular disease is called the Red Death. So the Red Death doesn't really closely mimic too many things that we have currently right now, but this would be a disease that is makes you contagious and sick for a long time, has extremely high transmission rate, and even higher death rate of 20%. So thankfully, there aren't too many diseases that follow this pattern, but this is just to give you an example. So again, you would look at medium population density, medium mixing, and you're going to alter these vaccination rates based on what's in your table. And then once again, this time we're only going to do 2 runs of each of these. And so you will go ahead and hit the run button. You'll watch the disease spread. And once again, you'll see what happens. So the maximum number of contagious, our number of deaths, our sick days per capita, all of this information you're going to go ahead and put into your table then, and then you're going to answer the questions. So again, I know there's been a few troubles with some of the simulations, the carbon simulation and the energy simulation, trying to get the energy that you needed and trying to figure out where you were accounting for the carbon. Of all the simulations we've used so far, I feel like this one is the most straightforward. So there really shouldn't be too many obstacles as far as recording your data goes. Just remember that you're specifically looking at the graph here, and you're also looking at the information up here at the top of your chart. So again, if you have any specific questions about the lab or the simulation, please let me know. But again, it's fairly straightforward and pretty eye-opening, especially in the midst of the world we find ourselves in now.